All right. First of all, do we have any questions about the project? Let me just try to explain it a little. Relatively speaking, question. So as you can see, the groups has been assigned, and unfortunately, we have 61 students, right? So the group 1 has to take 1 student extra. Group 1 is 6 students, and the rest of the group has 5 each, right? That's the ideal number of students, because what I found out is that if I assign more than 5 students in one group, I mean, it becomes a mess. So some of the students don't do anything, and it's not that effective, right? So first of all, can you guys all please check, make sure your name is on it, and then make sure your name doesn't repeat, okay? All right, anyone's name is not on this group table. Anyone? Okay, everyone is on it, right? Okay, so this will be the group you'll be working with in this entire semester, right? We'll have 3 projects, and I'll take half of the credit, half of the grade, right? So make sure we do a good job in group projects. Okay, so that's about the group assignment. So there's 12 groups total, right? So that's it. And for the project, as you see, project 1, relatively speaking, it's a very simple design problem. All you need to do is do some stress analysis and trying to optimize the design. All right. So the description is actually this is a backhoe we're using in Baja, and it's very simple. All right. It's the most simple element I can find on Minibaja. And I think it's a good start for you to start doing projects, because I'm pretty sure this is your first time to do some mechanical design projects, right? And eventually your principal design and the senior design will be way more advanced. And this is a good start, right? So, the given conditions are relatively simple. So you just consider that as static loading. So the tensile loading you have over here is 5,000 newtons, right? So by saying that is all you have over here the force you have on this buckle is 5,000 newtons. Of course, it's going to be 5,000 newtons going up and 5,000 newtons going down to make the equilibrium, right? Okay, and also we need to consider the nice safety factor. So I say safety factor 3.0. Exactly, so you can consider as 3 times of the load without failure of the materials, right? So the failure here we're talking about is just tensile strength, right? Because the only load we have is tensile loading. So possibly it's going to break at its weakest point somewhere, or where the stress is the maximum, right? Okay, so the only dimension I give you here is the slot for the strap is 2 inches long. So here's 2 inches. That's the only dimension I give you. The rest of the dimension you can design it by yourself. Okay, feel free. Materials can be any kind. Of course, if you choose stainless steel, the tensile strength will be high. But the problem is it's heavy, right? The density of a stainless steel is 7.8 grams per cc. While if you choose aluminum, of course it's going to be only 1/3 of the weight, because its density is only 1/3 of the stainless steel. Problem is it's going to be a less tensile strength, right? The tensile strength of aluminum will be way less than stainless steel. Of course, you can choose plastic if you want. It's really light material, but also at the same time, the tensile strength is low, right? So you got to decide what material you want to use. Yes?
Is cost a factor?
No, it's not. Yeah, we're not going to fabricate it. So use whatever you want, all right? You can use diamond if you want. As long as it satisfy the requirement, all right?
But nasty.
Okay, and Okay, so next is important. Expectations. You'll see expectations in the middle of the design requirement, right? Now it happens to have 5 expectations total, which is no accident because most of the time we have 5 students in one group, right? I want each student to take care of one of the 5 expectations. Okay? So for example, the first one is lightest weight possible without failure. So that tells you the buckle you design has to be really lightweight, but at the same time has to withstand the safety, so it doesn't fail. Okay. And the second one is a failure criteria. So yield strength. So we want to know how do we determine what's failed now, right? We want to find the yield strength according to this website I provide over here. I can show you what the website looks like. Because all we are considering here is yield strength. Come on. For those of you who are doing research in the lab, I'm pretty sure you know this website, right? McMaster. This is the website you buy lots of hardware and those metals as well, right? So for example, I say, hey, I decide to use stainless steel. So what I decide, see, hey, 304 is a common one. Probably I use 304. And then you come over here, just pick whatever you want, what shape you want. And it's taking a while. See here, yield strength tells you, right? 30,000 psi. So you just use that number. Okay? Make sense? All right, so go to McMaster. That's the website we get most of the materials from. All right. And the next thing is Cad Drawings. So blueprints. All right, after you design it, give me a 3-dimensional view blueprints. The idea is you take the blueprint to the machine shop. They should be able to machine it out for you without asking any questions. That's the requirement for blueprints, right? So number 4, perform load analysis using the FEA. Now, based on my experience, most of students like to use ANSYS because it's available to us through my apps at UTEP, right? Anyone can use it, and at the same time, it has built-in finite element analysis functionality, so you can use that, right? So just try to use ANSYS. Everybody knows ANSYS, right? ANSYS, just this one, all right? So I think it's in my apps. I'm pretty sure last night I checked, should be, all right? And last one is pick bolt and nut for the design too. So see in the bottom of this buckle, if you look at this picture over here on the top right corner, it has a bolt and nut at the end to fix this buckle, right? So you need to pick a bolt and nut and justify why you pick that based on load analysis and other things. Okay, you also can go to McMaster to find the bolt and nut. For example, I need a bolt. Just search here. I don't know, there's so many of them, but I need to pick one, right? But don't just pick one and say, hey, I think this one looks pretty. No, we're engineers, right? We're not liberal arts, right? You have to tell me why you picked that, right? Pretty doesn't count, all right? Okay, so you need to pick one, dimension, and what kind of thread it is, what's the diameter of the bolt, and what kind of nut you decided to choose, all right? So tell me why and justify it. Okay, so there's 5 expectations and 5 students. So each one of you try to take care of one of it. But all these 5 conditions are related, right? For example, Cad drawings and lightest way possible without failure. You need to determine the geometry of this buckle, right? After you determine geometry, you can tell the people who's going to take care of Cad drawings, say, hey, this is geometry I decide. So you go ahead, output the Cad drawings for us, right? Or for the number 4, perform load analysis using FEA software. After load analysis, you know where the maximum stress is at, and then you can tell the people who's going to pick bolt and nut, say, hey, maximum stress is around the hole in the bottom. Okay, so make sure when you pick the bolt and nut, the diameter is not too small, right? So they're all interrelated. So I want all of you to work like a team. At the same time, each of you will have some individual tasks. Okay, make sense? All right. So it's a good practice for all of you, okay? And 2 important dates. First of all, as you can see in the bottom, the review date is on September 23rd, 2014. September 23rd is 1 week from today. Right? I'll give you 1 week to think about it. And next Tuesday, today is Tuesday, right? Okay. Next Tuesday, we don't have class meeting, right? We don't have lecture. What I'm going to do is we have about 80 minutes, right? Entire meeting time, 1 hour and a half. Then we have 12 groups. So each group gets about 6 minutes, right? So I'll invite group individually. For example, I just invite group 1 first. And then you have to tell me who's going to do what. And then what kind of idea you have so far. And what kind of question you have so far. So therefore, I'll help you do a review of your design, right? You don't have to have a complete design yet, because I know 1 week is kind of short, especially for the first project. At least you have to get me some big pictures and get me some detailed tasks out. So therefore, I can make sure all of you are on the right track, okay? So design review is on September 23rd. And the next one will be a project presentation. Because we have 12 groups this semester, last semester we only had 35 students. This semester we have 61. So we have to separate the presentation into 2 meeting times, right? So September 30th, we will have group 1 to group 6. You need to come here to give us a presentation. And I encourage you to use PowerPoint. It's about 10 minutes of presentation, 2 minutes of question. So therefore, try to prepare about 10 slides to 12 slides at most of your entire project, all right? Starting from introduction, ends with the conclusion, right? So that's something we need to do. And on October 2nd, which is a Thursday, we are going to have groups 7 to group 12, okay? Now, if your group is not up for presentation, you don't have to show up for class on that day, right? For example, on September 30th, group 7 to group 12, you don't have to show up. But if you want, feel free. Either way is fine. Make sure, one thing I do require is when other people are presenting, make sure you're quiet. Don't talk. Okay? All right. So, oh, one more thing I forgot. So remember I said there's 3 different components for each project grading. That's the only useful thing I said in the psychology building, huh? What I mentioned is just buckle only, just that buckle, okay? So the only thing you need to design is a buckle. You don't have to worry about any other things. Okay, so I said for each project, 1/3 will be from your report. The other 1/3 will be from your presentation. Now, each group only need to submit 1 report, okay? The last 1/3 is individual, right? Report, because you need to submit a report while you're presenting, all right? So I need to grade them, and I'll give back to you, right? So that's a clear. Presentation is also clear. You prepare the slides, and then you do a presentation, you send me the slides, and then I will grade that, right? Individual, like I mentioned, it's based on your individual effort. So your group member grades you, right? Remember I said that? Anyone forgot? No? Okay. So individual is from your group members. Now, if you look at the group members roster over here, there's 1 space underneath each name, right? And there's a purpose for it, right? So for example, group 1, we have Andres, Carlos, Jeremy, Carlos, Danila, and Oma, right? So for example, Oma, his individual grade will be based on the rest of the 5 group members, right? So for Oma's grade, Danila, Carlos, Jeremy, Carlos, and the rest is going to write a grade for him, right? And then also by saying that, and the rest needs to grade the rest of the 5 group members grade, right? So in 100% scale, right? To 100, 90, 80, 70, If you really hate him, 0, right? Okay. Okay, so just do that. Make sense? Any questions about individual grade? It's clear, right? You grade every single other group member's performance, okay? And you don't grade yourself, okay? If you grade yourself, then you get 0 automatically. Okay, so any questions about the project?
The report, what's the format that you wanted?
I don't give a format for that, but usually, based on my experience in the past 2 years, it's about usually at least 10 pages, right? You have a cover page and the introduction, and then discussion, your design, and a conclusion and reference, right? So that's usually how it looks like. I can show you one of the example of the report. The reason why I don't do that is because just kind of like a research paper, there are lots of different format in writing this, right? I don't want to limit you on any specific things. So you just make sure your idea is 100% conveyed, then that's okay, all right? So report, this is I think from last year.
So 10 pages, that's what you wanted, or that's usually what you get?
That's usually what I get. If you can convey all your idea, you can have that in half page, that's fine with me, all right? Whatever you want to do. Let me see, PPT. I think it's on this one. Oh, okay, no, I only have PowerPoint slides here, I don't have report, but usually it's around 10 pages long, right? But be creative, whatever you like to do, okay? Any other questions? Any other questions about the project? No question? All right, then I'll have lots of questions on next Tuesday for you guys, okay? All right, one more thing before I start today is I'm trying to make a deal with you guys. If you look at the syllabus, we said we're going to have a quiz on September the 23rd, right? Can we change that to September the 18th? The reason is if we have quiz on the 23rd, then we have to do the review on the 18th, which I think is too short of time. It's only 2 days. What do you guys think? Can we have the quiz on December the 19th? Which is December, I won't even be here, right? Yeah. September the 18th, okay? September the 18th. So which is 2 days from today, quiz. Just 2 questions for the quiz. Now, if you all agree, what I can throw in is I'm going to do a review of the exam for you guys.
Today?
Not today, on the 18th.
Oh.
What? Didn't get it? Okay, here's the deal, everyone.
The exam stays on the 25th, right?
That's the only thing I want to change. Okay? Now what I can do, I'm going to do a review of the exam on September the 18th as well. So therefore you can prepare better. Okay?
That's if you change the date, right?
Huh?
That's if the date is changed from the 23rd to the 18th.
Right. Yeah, if you don't want to change, that's fine. We'll just have the quiz on the 23rd, right? Still, and we're going to have the review on the 18th.
And the exam on the 25th.
Huh?
So when will we have the review? If we leave it on the 23rd?
No review then.
No review.
Right. Who's against the change? Raise up your hand.
Solo.
That's all right. We'll let him take the quiz later on, right? We'll just take the quiz by ourselves. Now, How about, I think it's better because if you guys want, I can still keep the same, but we have to do the project review 2 days from today, which might be too short of time. Do you guys agree? You better have 1 week to discuss it, right? I mean, quiz is a quiz. That's just easy, right? And then, so on September the 18th, what I'm going to do is we're going to have a quiz plus exam review, right?
Review
So,
before the quiz?
no, of course after the quiz. Yeah. If I do the review before the quiz, you guys will be too excited, right? Yeah. But what I can do is I'll give you guys a quiz for 30 minutes. I'll do a review probably for 20 minutes, right? And then maybe a small example, so we can have the class a little shorter too, if you want. All right? Okay? All right. Okay, so that's done. By saying that, so be prepared. On this Thursday, 2 days from today, we're going to have a quiz, okay? And it'll be 2 questions, and will be very similar to the examples we have learned so far, all right? Should take you about 20 minutes to finish, but I'll give you 30 minutes to work on it, all right? Okay, any questions about quiz? Questions, guys? No?
Specifically, what subjects?
In terms of what?
For the quiz?
For a quiz? So you're trying to ask me to do a quiz review?
Yeah.
Well,
Just what subjects?
truth be told, I haven't made the quiz yet, so I don't know what it's going to be covered. So what do you guys want to have it in the quiz?
Some of the first stress and moment diagrams.
Sure, we'll have that.
Stress and moment diagrams. Don't listen to it.
Hate him, don't hate me, okay. Well, but that's something I think it's good, yeah. What else do you want to have? How about this? I love this question. Two-dimensional bending? What? No? What do you want to have then?
Some of the forces.
What? Some courses. I mean, we're not high school physics here. We're mechanical design. It's fine. Let me see what else we can cover. Oh, if you want, we can have something simple. We don't have this. This is complicated. We can have
The other one's better.
huh?
The other one's better.
What's the other one? The two-dimensional?
Yeah, two-dimensional.
You don't like tolerance?
No.
What?
So first thing we do,
How about I do something simple?
there you go.
The pretty much the first example. We'll have one really simple, one medium. How's that? We'll keep it all the hard ones to the exams. How's that? Okay, exams you don't get to pick, all right? For quiz you can pick. Just trying to make a deal with you guys. Since you guys is hard to satisfy. Yeah. How's that? We'll just have these 2 kind of questions in the quiz. Okay? All right. Okay. It's done. All right. Deal is done. All right. Oh, there's 2 things I found out about using iPad to teach. I asked Dr. Love, by the way. Your name is Diego, right?
Yeah.
Okay. Now I know you, right? You're the one saying bad things about my writing, huh? Okay. I asked Dr. Love. He said, what you need to do is just need to zoom in and write it better. So I try to do that, all right? And see how it goes. And then the second thing is, in the half of the department is trying to use iPad to teach this semester, all right? Now, what we all notice is when we teach this way, when we just sit here and write, we don't get that excited. So we don't show the passionate for the teaching, which is, well, I totally agree, right? So when I use Blackboard to teach, I feel more energetic and I can teach better. To be honest with you, I don't really like to use iPad to teach, but we have to because we're trying to move everything online for the lecture. So in the future, we can do more examples and projects in the class. So one of the alternative way they suggest is when we write, we don't sit, we stand. I can try to do that and see whether that's better, okay? Now, the rest of the time for today, I really want to use Blackboard today because the example I want to go over with you guys, the one we didn't finish on Thursday. But someone need to help me how to move this thing up. Because when I press up, it goes down. When I press down, it goes up, but it stops here. Anyone can help me? Diego, want to help? I don't know what it is. It's just for you. Maybe I'll just keep on pressing. See how far it goes. See, it goes back.
Maybe lift it away from the metal so it doesn't.
There you go. Okay, so the first half hour I want to use Blackboard. So let's use that. Back to the traditional. All right, because I got lots of questions at the end of Thursday's class, so I think there's some misunderstanding and some of the things I didn't explain right. So what I'm going to do is I'm going to give you a quick overview of the problems we did on Thursday, and hopefully that can help most of you understand. And we can move on, okay? All right, it's relatively speaking, three-point diagram. It's simple. So you have A, B, B, C, and at the end I add a point at C, D. All right. So three members. And A is fixed to the wall, and it's a static. There's no movement at all. Right. Now, the first thing that we are asking is what's the force bending diagram or bending moment and a torque applied to each member, right? So it's only one force applied to this structure. This force over here equal to 300 newtons. And the coordinates we have over here is we have X, Y, and Z. Right, that's all we have. You guys all see it? It's terrible, right? If I write over there, would that be better? No? Then what should I do? This is better, right? I assume. So first of all, let's look at CD. CD over here, we have a force equal to negative 300 J. Because all you have over here is I, J, and a K. Three dimensional coordinates, vectors. They're all unit vectors. Okay, so now for CD, it has to under equilibrium because CD is a cantilever beam, right? Okay, so I automatically know at point C, I have a force going up, 300 J newtons, going upwards to counterbalance for that, right? So all you need to do is these two things: summation F0, summation M0. Okay. Now, as a cantilever being, of course, at the end you will have a bending moment to counterbalance for the bending moment caused by the force F, right? Now, like I said, the moment caused by this F, use your right hand and use your four fingers, which is going down with the same direction as the force, and your thumb is direction of the moment. So this force is going to cause a moment going this way equal to 300 times the distance is 1.5. So 300 times 1.5, 450 Newton times meter, right? So therefore, at this point, you will have a moment that's counterbalanced for in the direction of K. Whenever you see direction, you just compare over here, right? Okay, so that's it for CD. Right? No question about this, right? Any questions? Give me some response. Don't have any questions?
Just mention that cross-sectional thing that you said last time.
Huh?
Just mention the cross-sectional thing that you said last time about the right-hand rule.
Oh, so you have a CD beam over here, right? CD. Now, some people telling me, oh, you use your right hand. That's cool. But if you're using this way, or if you're using this way. So the way you need to think is you have to make sure this beam goes through your hand from the inside, okay? So therefore, you have to use your hand in this way, because otherwise, it's going through your hand from the outside of your hand. Make sense? Right? Yes? Okay. All right. And we know the direction of this moment. It has to be the opposite of the moment caused by the force. Therefore, summation M is 0. Right? That's clear, yeah? Okay. Good. So the next thing is we come to BC. Okay, BC over here. First of all, using internal force or Newton's third law, we know at point C, you're going to have a different force with the same magnitude but different direction. So it's minus 300J going downwards, right? And in the same time, you are going to have a moment. I try to use double arrow over here with a magnitude of minus 450K Newton times meter, which this minus 300 and this 300 cancels out. This minus 450K and this positive 450K cancels out because it's all internal force, internal moment, right? So therefore, the summation of this total should all be 0. So therefore, this is my C reaction force and reaction moment. But like I mentioned, if this moment is 0 degree with your aligned with your BC, that's torque, right? It's going to cause twist. If it's 90 degree, see here the direction of your moment with your beam. If it's 90 degree, it's going to cause bending, right? Okay, so we know this is torque. So we look at point B over here. Of course, you're going to have a force of 300J Newtons going up to balance for the force. And in the same time, you have a torque of 450. Okay. Newton times meter, which is going to this different direction, but with same magnitude to balance for that torque, right? Okay. And in the same time, BC is a cantilever beam. So we have a cantilever beam, you have free force at the end, free end. You will induce a moment, kind of like this, right? See, you have a free force, you have a moment to balance for it. So in the same time, BC is also a cantilever beam. Now this time, C is free, B is fixed. So therefore, this force over here, 300J, is going to cause some bending moment. So at point B, you have a bending moment to balance for it. Now the amount you need to find out is BC. The length is I believe 4 meters long, right? Okay. So 300 times 4. Again, use your right hand. So goes down like this, right? So this moment the direction caused by force is going backwards. Okay. Now going backwards, that's a 300 times 4, 1200 unit times meter, and in the direction of negative I. Therefore, at this point over here, at this point B, you gotta have a 1200 I Newton times meter moment to balance for it, right? So you have three things at point B. You have a force 300, you have a torque of 450, and you have a bending moment of 1200. Direction all opposite to this direction at point B. And the only thing is the moment over here is trying to balance for the moment caused by these 300 newtons. So therefore, it's pointing to the positive I. Okay? Again, all I'm using is the only thing is one whole thing introduced called torque. Right? Clear? Questions? Concerns?
Professor,
Yes.
the first one, why you represent the moment in the opposite way of the real force?
So this thing over here,
So, the first one,
this thing here,
yeah, because the first force was a moment in negative z.
right? Yeah.
Why you represent in the other way?
Oh, okay. So all you're doing here is summation m is 0, right? So if I say here I have a moment of mc, okay? So from this equation, what do you have is mc plus whatever the moment caused by this f, which is a 300 times 1.5 in the direction of negative z, which is minus k. Agree? Right? This is moment caused by this force. This is a moment existing at point C. So the total moment has to be 0. Yes? Okay. Now from this equation, you can see mc just equal to 300 times 1.5, 450. Minus k, move it to the right hand side of the equation, becomes positive k with a unit of Newton times meter. Agree? Okay, so that tells you mc equal to 450 k Newton times meter, so which is positive z direction, right? So the way I just did it because I think by looking at a question it's confusing because you don't know which one is positive, which one is negative. Now the way I did is I look at this plot, look at this figure here. So this force is causing moment going backwards to negative z. So at a point C, you gotta have another moment to balance for it with the same magnitude but different direction. The magnitude I calculate out from here, 450, and direction. See, this direction is positive k. So 450 k Newton times meter. Now this doesn't really existing in point C. The reason why I draw it is trying to let you know what's the bending moment caused by the F applied on point C. Make sense now?
Why are the moments being represented by straight arrows instead of a curved arrow? Because usually
Curved
that
arrow,
tells us-
what do you do is only in two-dimensional. We are looking at three-dimensional problems now, right? So therefore, we're using double arrow to representing the direction of the bending moment. Make sense? Because all you guys learned before is in two-dimensional. Therefore, the bending moment, for example, a beam on a curve, we just say it's like that, right? In reality, think about this. If it's three-dimensional, this is your rotational direction, and the thumb is the direction of your bending moment. Okay, so that's why we're doing this. We're using double arrows. You guys learned that in mechanics materials, right? Yes?
Yeah.
Remember that? Torque, there's two double arrows, right? How did you guys pass mechanics materials, huh?
The
Right.
moment is like
Okay. Who taught you mechanics materials? I need to give that person a hard time.
That was 2 years ago.
Huh?
I took it 3 years ago.
3 years ago? Oh, sorry, I'll forgive you on that. Okay. So,
Civil too.
huh?
There's the civil.
Really?
Yeah.
Civil? Uh-oh. Did I insulting you last time? No, you didn't show up last time?
I'm not civil.
No, the teacher is civil.
Oh, okay. Man, we have a mechanics materials class. Why you took that with civil? Okay, but the reason is because we're doing 3-dimensional, so therefore we use a double arrow to representing from the moment. Okay, makes sense, right? Okay. All right. So BC is done too. The last one is the hardest. AB. So AB. First of all, point B is on both BC and AB. So if you look at it here, all the reactions on point B over here will be offset to that. So you have negative 300J newtons. And then over here, you have something going to negative 1200 I. Newton times meter. And at the same time, you have 450 going that way. 450 negative K Newton times meter. Right, so this is at point B of beam AB. Force is going down, torque is going in, so it's twisting this way, right? And again, the torque is the same thing. 4 fingers of a rotational direction, thumb is the direction of the torque, right? So for example, this one, the torque is going this way, right? So it means it's rotating in this way. Now back to your question, if you want, before what we did is we have a torque force, right? Torque, we use this kind of curve, right? But use your right hand. 4 fingers, rotational direction. Thumb is the direction of the torque. Okay? All right. It's because this is 3-dimensional. So if you draw all these kind of half curve, it gets so messy, right? The real direction is determined by the thumb. Okay? All right. Well, that's a really good question. Okay. Yeah. So therefore, everything here is trying to balance for everything here. So 3 different components: force, torque, moment. Okay, for point A, it's the same thing. You have a torque over here, 1200 I Newton times meter. To balance for the torque over here. You gotta have a force going upwards, 300 J to balance for the force. And then eventually you have a bending moment of 450 K balance for the bending moment, right? This is what we have. And one more thing is, don't forget, AB is also a cantilever beam. So remember what I said? When you have a cantilever beam, you have a force applied on the free end, you will have moment induced. Same thing. At the free end, we have a 300 J newtons of force going downwards. The length of AB is what? 5? What's the length of AB? 5. Good. So 5 times 300. Therefore, you have bending moment of 1500. Again, use your right hand going downwards. 5 times 300. That's 1500. In the direction of negative K, Newton times meters. So therefore, at this point A, you will have another moment equal to 1500 K Newton times meters. To balance for it. Okay, so the total bending moment at point A is 1500 plus 450 K because they're in the same direction, right? That's it. Any questions? Now we're clear, right? The only thing is cantilever beam, force is applied to free end, you will have a bending moment at the fixed end. Okay, that's the only thing you need to remember. All the other is just internal force. Summation F0, summation M0, summation T0. That's it. I don't really like to use equations anymore because when you have three-dimensional, direction gets so confusing. So I just do everything by looking at the figure. Okay. Now, if you still feel you can get the right answer using this, feel free, kind of like what I did, right? But I totally think when you look at the figure, it's more clear. Okay. Yes.
So the bending moment causes the torque, right? Is that what you're saying? Because at first I thought those were both moments.
Mhm.
They were both represented by an arrow with double head,
Right.
double arrowhead.
Yeah.
But now I understand one's a torque and one's a moment.
Exactly.
So
Yeah.
that was
Now another example you can always think is when you use a socket, try to tighten a nut, or you try to wrench to tighten a nut. What you apply is a bending moment to the wrench, right? So, for example, when I draw something like this, they're very good at drawing, right? So something like this, we have a wrench trying to tighten. Not very good drawing, but you get a point. Okay, so let's say this is long. All right, so we're trying to apply force over here, trying to tighten the screw, right? So the moment you need to use to tighten the screw is torque, because you're trying to twist it, right? You're not trying to bend the screw, right? Okay, you're trying to turn it, so therefore you need a torque. But you apply force here, right? The force applied on the wrench is bending. Make sense? So you apply force, get a bending moment to the wrench, transfers to the torque of the screw, so the screw gets into the wall or gets into the hole. Make sense? So by saying that, if your beam is 90 degrees apart, torque and bending moment, they're changeable, they're interchangeable. Your torque is my bending moment, my bending moment is your torque, because you see over here at point B, right? Point B, 450 is torque for BC, but this 450 here is bending moment for AB, right? And 1200 over here is bending moment for BC, but here this 1200 is torque for AB, because they're 90 degrees apart, right? Makes sense? More confusing?
it's perpendicular to torque.
All right. Well, see here, moment. If it's 90 degrees to the beam, that's bending, right? And if it's a 0 degrees to the beam, that's torque. That's it. That's all you need to remember, right? Okay. So so make sure you understand this example, right? It's a very important, and I'm very sure you'll see this in the exam. All right. Okay. Any questions? Yes.
Would it likely to be diagrams like this without 90 degrees on the exam?
Are we going to have that?
Yeah, like different angles? Or
Yeah, absolutely. Yeah. Otherwise, what's the point I spend almost 2 meeting times to explain this, right? It's important. Okay?
Well, no, that's not what I'm asking. I mean, are we going to have like to have not 90 degree angles?
No 90 degrees? Now. Like 80 degrees or 70? Now.
Okay.
We're not going to do that. No, we're not going to do that. That's too complicated. That you have to use some FEA to solve for it. All right? Okay. So, so that's pretty much what I want to say today, because this is a really important example. I want to make sure every one of you understands it. All right. So the rest of time, I'm not asking you to going home. All right. What you need to do is try to stay a little longer, maybe 5 minutes, 10 minutes. Try to talk to your group members, get to know each other, and then have some initial discussion. Okay. All right. I'll see you guys on Thursday. Yes.
Oh, no, we're just pointing at the board.
How's my writing on the blackboard? Oh, what I'm not already Silas, I haven't wrote this. I can't pictures. So that's when I write. Maybe it's Here is your
They should.
here's your natural way of writing. Here's your natural way of writing. Just do this, right? It doesn't work. I have to write like this. Yeah, but that's a problem. That's why I'm trying to, they told me the Analysis-MECH that doesn't get signal from the gate, so you can just write like
Okay, so this is CD, right? Mark CD. It's about X.
Oh, I know that one.
It's easy just to memorize.